A stone is dropped from the edge of a roof and hits the ground with a velocity of negative 200 feet per second. How high in feet is the roof? It's kind of a surprising question. So they're saying if you just know how fast the rock is going, the stone, when it hits the ground, that's the velocity, the speed with which it hits the ground, you can know how high up the roof was from which it was dropped. Can you really do that? That's interesting. Just by knowing the speed, like if you have like a radar gun, that shows like for pictures or for traffic when they record how fast something moves, you can just find the radar gun for the speed when the stone hits the ground, you can automatically calculate from that how tall the roof is. Yes, you can, using physics and the knowledge of the gravitational acceleration of the Earth. So let's do it. So first off, we got to know the relations here. We start with S, which is position. I don't know why we use S for position, but we do. And then we go on from there to V, which is velocity or speed. Same thing, basically. Velocity is just speed with the direction, your physics teacher will tell you. And A is acceleration. That's the rate of change of velocity. So what we know is if we to go from speed to velocity, we take the derivative, and from velocity to acceleration, it's the derivative. So then vice versa, from acceleration back to velocity is the anti-derivative. From velocity back to position is another anti-derivative. So it's the opposite process. So we're starting with the Earth's gravity is that. So that's acceleration due to the Earth's gravity. So we're starting with acceleration is minus 30. It's minus because gravity, Earth's gravity pulls everything down, negative. So now to get from acceleration back to v velocity, you know what we got to do? We got to do the anti. So I'm going to do the antiderivative, and that's going to be minus 32t plus a constant, right? Because if you took the derivative, minus 32t, it'd go back to minus 32, and the constant would go to 0. So there could be any constant number out here that doesn't have a letter, just a number. Okay, now let's stop right there and see if we can find that. It says it hits the ground with a velocity of negative 200. Okay, so the velocity when it hits the ground is negative 200. So, with that in mind, well, no, actually, no, we're not ready for that. Hold on, let me go back here. What's the velocity when it's dropped? That's what we're going to start with. So notice it says the stone is dropped from the edge of the roof. So do you realize that means it's dropped? Notice it's not thrown up, it's not thrown down, it's just released, dropped from the edge of the roof. So sometimes you'll have problems, physics problems, where they throw something up or they throw something down. This one's just dropped. What does that mean? Velocity is 0, right? When you drop something at time 0, meaning right at the start of this situation, they dropped the stone, meaning it had no velocity, at least at the start, at time 0. So that means velocity is 0 when time is 0, right? Plug in velocity time. And so now we can solve for C1. That's easy, right? C1 must be 0. So now we know more about the velocity equation. We can come on down and go, okay, so now the velocity equation is minus 32t, since C1 must be 0, right? We know C1 is 0 because why? Because the stone was dropped. So the starting velocity was 0. When you drop something, the instant you let go of it, it's hanging there in space for just a split second with no velocity at time 0. So the C1 is 0. Okay, great. Now we're ready to come over here and go, okay. And it hits the ground with velocity negative 200 feet per second. So when the velocity is negative 200, the time is it hits the ground. So we can solve for that time now. So let's divide by negative 32. We're going to get time equal. I'm going to go to Desmos here. I was not prepared to get Desmos, so let me do that. Um, Desmos. Oops, I don't want the graphing calculator. That was another mistake. Um, I want the scientific. There we go. Okay. So the Desmos scientific calculator. So I'm going to type in what? 200 over 32. I don't need the negatives. 200 over 32. And I get 6.25. So that means at 6.25 seconds, that's when the stone hits the ground, right? 6.25 seconds. How did I know that? Because I had the velocity equation at any time, and I know the velocity is negative 200 at the time the stone hits the ground. So I solve for that time. 6.25 seconds. So that stone takes 6.25 seconds from the time it's released on the top of the roof to hit the ground. So with that, we can now calculate how tall the roof is. Let's see how to do that. Let's go back to the V equation again. Minus 32t. Sorry, my it doesn't look so good there. There we go. Okay, now let's take that and go all the way. Let's to position. And so you know that means we're going to do an anti-derivative to get from velocity back to position. It's an anti-derivative. So what's anti here? This is first power. So let's take that minus 32, going to add 1 to the power, be t squared, and then divide by that 2, plus constant 2. Okay. So now, back up here. So now we have the position equation is minus 16t squared plus c2, just simplifying that. And this again is the position. Well, what do we want to know? We want to know the position at, at time 0, the position S is equal to the what? Top of the roof, right? We want to find at time 0, what is the position? Well, what do we know? What do we know? We know that at time 0, the position of the stone is at the top of the roof. So this is the position equation. And so we also know at t equals 6.25 seconds, the position of the stone is 0, right? It's on the ground. So we know 2 things about position. Let's start with this one. At time 6.25 seconds, the stone hits the ground. So if I take that S and I plug in 0, hits the ground, and I take that T and I plug in 6.25 seconds, then I can solve for C2 because I know the height is 0 at 6.25 seconds. So then that means, let's go to Desmos, minus 16 times 6.25 squared. So minus 16 times, I use my answer squared. And I get negative 625. Negative 625 plus C2. And then just bounce this to the other side. Positive 625 is C2. So now I've got the position equation. Let me bring it down. It is minus 16t squared plus C2, which I now know is 625. There's the position equation. Now the final thing we're going to do, really I should just move this down here, is we're going to say at t equals 0, the S, the position, equals top of the roof, right? That's where the stone's position, is going to be the top of the roof when t is 0. So if you plug in 0 here for t, that just goes to 0, and the position is 625. And so that must be the height of the roof. You see how I came up with that, right? Where did the stone start out? On the top of the roof, and then they dropped it. So at time zero, the position of the stone was the top of the roof. So if I plug in time zero, the position I get will be the top of the roof. 625. The stone was 625 feet up at time zero. It was at the top of the roof. So the roof must be 620 feet high. And so, recapping then, what did we do? We took their information, started with the acceleration, did the anti, got to this, but then we knew the starting velocity was zero because they dropped it. They didn't throw it down or throw it up. So we plugged in zero, found C1 was just zero, then we had the velocity equation. And then we knew it hit the ground at negative 200. So the velocity is negative 200. Solve for the time. So we found the time when it hits the ground, 6.25 seconds. Then we did an anti, got the position equation. We plugged in that 6.25 seconds and knew at that time the position was zero. So we could solve for C2. Now we had the complete position equation. And then we just needed the position at time zero because that's the top of the roof. It started at the top of the roof. That's 625. And so there we go.